Okay, so we said we are going to go over stoichiometry basically. Okay, so I'm sure we've already done this topic. Some of us are already even on the third topic as chemical bonding, right? Others have done gases already, done atomic structure, and doing chemical bonding now. So I'm sure we have ideas. So I'm just going to give you a summary of everything that you've talked about in the simplest way possible. Okay. So what are we saying? What is stoichiometry basically? What is it all about? It's basically gives you the foundation of what you're going to be covering in chemistry. I think I've always been mentioning to say, as you get to look at this topic, you're going to notice that as you edge over to analytical chemistry, electrochemistry, it is based on this very topic. So if you don't understand it from this point, it will be very difficult for you to understand what we're going to look at later on. Okay, so basically what do we get to look at under this topic? We get to look at the study, or we study just the amounts, that's all. If you've noticed what you've been talking about under this topic, you just study the amounts of the products and the reactants. That's all. So now what do we basically mean when you say studying the amounts of the products and reactants? So this is a case where you're now trying to look at things like determine how much was produced in a chemical reaction. So I like giving this example where I have such two, A and B as your reactants, to have C and D as your products. So stoichiometry basically, it only gets to assess you on the idea of you getting to understand what all these are all about. Like from the issue of determination of the number of moles, of course by looking at what you've been given. If you've been given solids, if you've been given solutions, we're going to talk about that. So it is also very important for you to understand what we call the mole ratios. These are very, very important. Okay, so we're going to talk about all those things and how we get to look at them. Okay, so now under stoichiometry, they're going to assess you on things like determine how much of D is produced, and for you to determine anything in the reaction that is either reacting or how much is produced, you need to identify what we call the limiting reagent. So at the end of this lesson, you should be able to determine what we call the limiting reagent and understand its importance and how we get to use it in our calculations under stoichiometry. So the limiting reagent is very, very important. And also we're going to understand determination of number of moles for solids as well as solutions. Okay, so a component called solution stoichiometry, which involves you dealing with concentration and volume, that is also very, very important for us to look at. Okay, and some many more things like getting to balance the chemical equations using different methods, being able to convert from atomic mass units to grams, and also being able to... Are you getting me? You're too quiet. Okay, and also being able to deal with the aspect of you, dealing with ion electron method and calculations and other things. Those are very, very important. So we can go over now. We even talk about the isotopes. I'm sure that is also a very common question that we get to look at. So basically that is what this topic is all about. The aspect, of course, even a point where you get to talk about percentage purity, you get to determine the percentage purity and everything else. So let's get to look at all that. Let's get started. So I'll start from the issue of you being able to determine the number of moles. Okay, which I feel you already know. But we'll make it so simple. Okay, so I'm sure at this point you basically know that we get to determine the number of moles. Okay, as what? Well, so when you're talking about solids, you're going to look at the mass basically that you've dissolved. So it's going to be the mass over what? The molar mass of the compound that you have. So I'm sure at this point we do understand that the molar mass, it can be the molar mass as we've said. It can also be the relative molecular mass in a case where you're talking about what? Where you're talking about a compound. For example, if you talk about calcium carbonate, for instance. So calcium carbonate, basically, for you to determine, we don't call what you're going to calculate as your molar mass, we call it the relative molecular mass because it involves you determining the average of what? Or basically the total relative molecular mass of the molar masses of each atom or element part of that compound. So I'm sure we do know what to do there. So you need to look at your periodic table, identify the number of atoms of each element that you have, of which in this case we can see that oxygen we have 3. You multiply by 15.994. You go to the carbon, which is 12.01. You go to the calcium, that I believe should be something like 40 something. Okay, so if you get to hard, approximately you're going to have 100.01 grams per mole. Okay, so this is one aspect that is very important as you get to look at the number of moles. And this is a case where you're talking about a solid. I'm emphasizing you're dealing with a solid in such a case. And the mass, of course, is going to be given. So that's how you get to determine the number of moles. Okay, that's very simple. So I basically use a triangle to help remember all the formulas that you get to work with under solids. So where you're going to say the number of moles denoted by N is basically equal to the mass over what? The molar mass. So this is the triangle that you have. So all the formulas are coming from here, implying that your mass is just a product of the number of moles and the molar mass. Then the number of moles is mass over what? The molar mass. That's the way you get to look at that triangle, and it will help you basically to remember all the formulas that you can. Alright. Now the other aspect is what we call solution stoichiometry. So the only difference is here you are dealing with a solution. So instead of you dealing with the masses, you're going to deal with what? The concentration. So it basically starts from you understanding what concentration is all about. So what basically is concentration? So concentration is basically defined to be the number of moles that you get to dissolve in what? So number of moles dissolved in what? In a solution. So the number of moles that you dissolve in a solution is what we call a concentration. How many moles are in this given solution? That's what you need to think of when you're talking about concentration. And the most important unit of concentration that we're going to be looking at is what we call a molar concentration. Okay, so I'm sure you've come across something what we called molar concentration. So molar concentration, basically I can just also say molarity. Okay, so molarity basically is defined to be the number of moles. Okay, so number of moles dissolved in a liter of a solution. So this is more specific because we're dealing with a solution that has got its volume given in what? In liters. So whenever you look at this calculation, number of moles being given as the number of course, let me talk about concentration. So you're talking about concentration as the number of moles dissolved in a liter of a solution. So when you have moles on top and then you get to have your volume in liters, what you have is in molarity. Are we together? So basically molarity is just one way of expressing concentration, but concentration is more of a general term referring to the number of moles dissolved in a solution. So concentration is general, molarity is basically specifies the units that you're dealing with, that is moles per liter of a solution. You can also say decimeter cubed. Of course, decimeter cubed is basically equivalent to a liter, so that is also okay. They all refer to what? Molarity concentration. Do we have any questions at this point? Okay, just before we can get to determine or calculate any number of moles here, I just want to emphasize that you can also use dimensional analysis to make your work easier. So in a case where they give you the concentration, to say you've been given 2 molar concentration, and then they also tell you the volume is so 2 molar concentration of a certain solution, then its volume has been given to be maybe, let's say, 4 liters, right? How do you get to find the number of moles in that volume? Kindly mute your mic. Petronella, mute your mic, please. Okay, so we can move now. So we're saying the number of moles. So remember I said our formula is what you're looking at is concentration is equal to number of moles over what? The volume, right? So if you make number of moles to be a subject, you have that. So I usually show these formulas, not that I like using them, of which I never did. I don't like using the formulas. So let me try to show you the aspect of you getting to work with dimension analysis to make your life easier. So you basically understand that that is molar concentration. So it basically tells you that you have 2 moles per what? Per liter of a solution. So you have also 4 liters there. So looking at that, analyzing the given data, what you want is, you just want to remain with moles, right? So you can just, what you'd want to do is, since this is part of the denominator, you'd want the other one to be on top so that they're able to divide and cancel out. So you just multiply by 4 liters, and these are going to divide, right? Then you remain with what? 8 moles. Even in the other aspect, of course, let's take an assumption to say, of course, you've been given the number of moles, and then they also give you the volume. They ask you to find the concentration. So you basically understand that concentration, you'd want it to be moles per liter, right? So you already have the moles there and you have the liters there. So you just get to say, okay, I have 8 moles. I can multiply by a reciprocal of what? The volume. So that I can have moles per liter. That's how you get to work with dimensional analysis. And this is what basically your lecturers want you to do, rather than writing the formulas and memorizing them. Okay. Look at the units, understand what units denote what. That will make things easier even for on your part. Okay, so do we have questions? Do we have any questions? Where are you lagging? Is there any part that you'd want me to repeat? Okay, I'm too fast. Okay, am I too fast for everyone? Okay, I'll slow down a bit. Okay, so now at this point we've seen how we get to determine the number of moles in both cases, right? In a case where you are given a solution, and also in a case where you are given a solute dissolved in you're given a solute, of course, yeah, a solid and also solution. So have we seen the difference here? Are we able to distinguish the two? So I hope you guys are not in a panic mode, because you know when you're in a panic mode, you basically you can't even understand. You just want to, you know, I'm sure we understand what you're going through. Maybe in a case where maybe you you feel you are very much behind, and you don't want to spend time on stoichiometry, and you just want to do what you've covered in class, and you want to be up to date. So basically that won't help you in any way. It's basically very important to understand the starting point, the basics. Build from the basics. Don't look at where your friend is, where the lecturer is. Make sure you've understood from where you started. So don't rush to move to new topics when you've not understood the basics. I know some of you are like, he's teaching this, and then you just want something that is, but you've not understood the basics. So it's very, very important that we build up from this stage. So just stick around. Okay. So now let me try to add the more ratios there to see, we basically get to understand why they are important. Okay. So now let's say we have maybe a 2 there, and maybe I can put something like 3, and maybe a 2 there. And then they tell you the molar mass of A is maybe, let's say, 20 grams per mole. Then the molar mass of B is maybe 30 grams per mole. Okay. Then of C you have been given maybe, let's say, 40 grams per mole. Okay. Then they tell you to say, so I'm going to start with So the fact that I've given you the molar mass here, we want to look at solids first of all. Let's say, so we've given you the mass. Let's say for A you have 2 gram. Maybe let me say 2 gram of A and 2 gram of B. Then now, question 1 is calculate what? The mass of C produced. Okay, that will be a first question. Maybe a second question is calculate maybe the mass of the excess reagent, maybe unused, right? Or the one that doesn't react. I think these two questions are very, very cardinal for us to basically understand the mole ratios. Okay, so to start with, the most important thing is that whenever you are trying to predict how much of the products were produced, it's basically very, very important that you get to look at the limiting reagent, because the limiting reagent is one that basically gets to limit the amount of products that you have. Why? Because it's basically gets to finish faster. Okay, so now in this case, for us to get to do that, we've been given the actual masses of the reactants, 2 grams each. So the fact that they are 2 grams each doesn't mean that they are all going to finish up. No. So we need to determine the number of moles and then use our mole ratios to compare which one and get to see which one is basically limiting in our reaction. Okay, so let's do this. I'll start with A. Our number of moles is going to be given as a mass over what? Over the molar mass, right? So I have 2 grams over what? 20 grams per mole. So if you divide there, what do we expect to have? You have something like a 0.1, right? Moles. Okay. So of course I'm trying to emphasize on the aspect of you getting to work with dimension analysis, which you can approach in this way. You have 2 grams, yeah? Okay. So grams per mole. So you have 20 grams per mole. So it means it's something like that. So what you want is you want number of moles. So you can write that as a reciprocal. You exchange them, right? The moles goes on top. So the 20 grams will go down there, which will imply that even if you don't know the formula, you can still come up with your answer by dividing the grams, divide the 2 by the 20, which will still give you 0.1 moles. Okay. So we have the number of moles of our A. We can also now determine the number of moles of what? The number of moles of B. So the question is, what mass do we have? We still have 2 grams here. So multiply by the molar mass was 30 grams per mole. So now we want the moles to be on top, so it will be reciprocal, which will give us what? Mole per what? Mole per 30 grams. So divide the 2 by 3. What are we going to have? 2 by 30, sorry. Calculator. So you can help us do the calculations if you have a calculator with you. So 0. Okay, so 67, that's fine. So we have our moles for A and B. So now, I'm trying to emphasize on the fact that what we've just calculated there is what? What we are calling the actual number of moles present. So we have the actual number of moles. So now, we are going to work with the mole ratios now, understanding that A and B are in the ratio of what? 2 to 1. As we can see that there's a 1 there. When there's nothing that is shown, it tells us to say that there is a 1, not so. So we have a ratio of 2 to 1 there to start with. So now, I can decide to get any. So I can get 0.1 and show it under A since it's for A. Then I'll now try to determine how many moles of B are required by A. Okay, so I'm going to have 2x here being equal to 0.1, and after dividing, my x is going to be what? 0.1 divided by 2 is going to give us a what? 0.0 what? 5, right? Are we together? So we're going to have 0.05 moles. So now these are the number of moles of what? Of B that are required by 0.1 moles of A. Get that point clear. These are the number of moles of B that are required by 0.1 moles of A. And we said what we've indicated down there is basically is denoting, or our values that you have down there are denoting our what? Are denoting our actual number of moles in the reaction. So since we have the actual number of moles, and now we are trying to compare to how many moles are required. So these are the moles that are required, and the actual number of moles are that. So now the question is, which one is bigger? Is it the required number of moles or the actual number of moles available in the reaction? Anyone to answer that question? You're lost. Where are you lost? Okay, so we just, what we did, madam, is we just like, I'm sure you are able to see the ratios, right? So we're looking at 2 and 1 there for A and B. So they're in the ratio of 2 to 1. I'm just getting the coefficients here. We call them stoichiometric coefficients. So we have 2 and 1, which we also call more ratios. So they're in the ratio of 2 to 1. So now, I said at this point you can either get for A, there's no restriction. You can either get for A or for B, and basically get to determine the number of moles of the other reactant required. So in this case, for me, I decided to get my A, which has 0.1 moles. So I'm trying to determine the number of moles that the 0.1 moles of A requires. So we've basically, we crossed and multiplied there. We had the 2 being multiplying by the x, giving us a 2x. Then the other side 0.1 by 1, which just gave us 0.1. Then if you get to divide by 2, our value of x basically we got 0.05, giving us or telling us to say that these are the number of moles required to react with the available number of moles of what? A. Now the question is, are these number of moles required, are they more than the actual number of moles of B that we have, or they are less? Okay, so since they are less, what can we say? Okay, B is the emitting reagent. Aren't you mixing up things? No, look at this. Approach this question in this way. The required number of moles are less than what is available. Meaning that what you have is more than what? I think that can make you, yeah. What you have is the required number of moles are less. What is needed to react with the available number of moles of A? Only 0.05 moles. That is what is required only. Now, what is required is basically less than what is available, meaning that what you have is more than what was required. What does that mean? Okay, basically that would. Oh, okay. Okay, B does have some excess moles, yes. But what I don't want to you guys to get is the fact that it's not a fact that if you have two reactants, A and B, for example, it doesn't mean that the one having the greater number of moles is in excess in every case. What would determine that is the number of moles, is the mole ratios, which in this case we are trying to look at. So let me just repeat one thing. Maybe people are still not clear. I'll repeat. Pay attention. Pay attention. So we were using the information given in the question to determine the number of moles, okay? So this is for our A. Then these are the number of moles available for our B. So I was saying these are what we are calling the actual number of moles. Is there any question about that? We use the given information in the question, the molar masses, and as well as the actual masses, of which there were 2 grams each. So we just divided by the molar masses to get the number of moles. Is that okay? Okay. So now we're trying to understand the importance of adding what we are calling the mole ratios, right? So we are saying A and B are in the ratio of 2 to 1. Can you see that? So we can clearly see that the stoichiometric coefficients are 2 and 1 for A and B respectively. So now I said you can get any of the two, either A or B. So I decided to get my A. I said, okay, I can work with B this time around. That says no harm. So I can also get 0.0667. Then now, what I'm using, remember, is these are the actual number of moles. So I'm trying to see whether these number of moles are going to react with A completely. So the value of X that I'm going to find will give me the number of moles of A required by the available number of moles of B. Okay? Is that okay? So what are we getting there if we cross and multiply? So it's like you're getting to double that. Mm-hmm. 0.06667 multiplied by 2. No one is having a calculator. Draw points. So these are like the number of moles of what? Of A. Get that point there. These are the number of moles of A required by what? By 0.066. Okay. Let me write that again. Required by 0.0667 moles of what? Moles of B. Are we together there? So now, let me repeat again there. So this is the point that we are making for own information. These are the number of moles that are available, actually available for B. So now we've determined that these number of moles of B, they need those number of moles for them to finish up. Okay? Now what we have in the question is we only have 0.1 moles of A. So meaning that the number of moles that are required are basically more than what we have of A. Meaning that A was not enough. And we can say A is what? Limiting. Have we understood? Have we gotten that point there? That's okay? Alright. That's good. If you just know now how to determine the limiting reagent, then everything is simple for you, because this is like very, very important. Very, very important. You can't predict the products if you don't know how to find the limiting reagent. So we've identified A to be the limiting reagent. That even as we get to answer our question, which is requiring us to predict the amount or the mass of C produced, look at the mole ratios. So they're in the ratio of 2 to what? To 3, not so? That is, we're comparing A and C, not so? So they're in the ratio of 2 to 3. So now the question is, what number of moles do we have for A? We have 0.1, not so? So we use the limiting 0.1 moles and predict the number of moles of A that are going to be of C that are going to be produced. So if you get to cross and multiply, what you're going to have, you have 2x being equal to 0.1 multiplied by what? 3 there. So 0.3 divided by 2. Kindly mute your mic. Hello? Okay. Ben, I don't know, Bendit. Help us with by muting your mic, please. Okay, so what are you getting after doing your calculations, huh? So these are the number of moles of what? Of C, right? So remember, in the question we are also given the molar mass of C, not so? So I'm sure we now have 40 grams per mole, and we have 0.15 moles. We want to find the mass. So you can just multiply these so that the number of moles can divide and remain with the grams on top here. What are we going to have? 6 grams of C. Is there any question there? What mass are we calculating? We were calculating the mass of C that was going to be produced in the reaction, and that's what we have. Okay. So what do I do now? We've answered our first part of the question. What was the second part of the question? Trying to determine the mass of the excess reagent that was not used. So in this case, we've seen that basically our limiting reagent or our excess reagent was B, right? It was more than enough because it needed more number of moles of A than what was provided. So I'll still use the limiting reagent to find the number of moles of B that reacted. Of course, taking note that our actual number of moles of B that were available from our calculations, of course, we said 2 grams divided by the 30 grams, right, per mole. We add 0.0667, right? Those were the actual number of moles. So now let's try to use the limiting reagents to determine the number of moles of B that are going to react. So these guys are in the ratio of 2 to 1. Then we'll put an X there. So we're going to have what are we going to have? So our X is going to be 0.1 divided by 5, which is basically 0.05. So these are the number of moles of what? Of B that are going to react. Not so. So there are two ways of approaching the question at this stage. You can use this number of moles and the molar mass to find the mass that reacted, and then get to subtract from the actual mass. Or Subtract the number of moles that reacted from the actual number of moles and find the mass using the number of moles that never reacted. Any question there? So our mass that reacted is going to be given as a product of 30 grams per mole multiplied by 0.05 moles. What do we have? Hello? 5? 1.5 grams. So we know that the actual mass that we had of B was 2 grams, right? You can subtract, and what you're going to have is now the mass of the excess reagent that never reacted in the reaction. Is that okay for everyone? You're not responding, so how do I move on? I'm not sure if you've understood or you're confused. Okay. So we've now talked about the more ratios and their importance, and also looking at the calculations to deal with all those calculations. So now, what is remaining is to get into details and get to talk about the different ways in which we get to approach our concentration. We can talk about things like, of course, we've not talked about parts per million, we've not talked about parts per thousand. We need to talk about that. Getting into details as well, to talk about, instead of molarity, we can now talk about what we call, okay, this one will involve you dealing with the masses. Then the other thing that we need to talk about is the issue of balancing redox reactions. Okay, balancing redox reactions. Looking at isotopes, dilution. So under the isotopes, we need to understand basically how we get to now determine what we call the relative atomic mass, right? What else do we need to look at apart from that? The aspect of you being able to find their percentage what? Abundance using the relative atomic mass of the isotopes. Okay. Are we together? So these are the things that we've not talked about. Of course, talking about the redox titrations. Of course, also balancing. Under balancing, there we have two methods that we get to work with. Okay. But for this afternoon, we just end here. This was just a trial. So for the people who want to register for the catch-up class, you can get to inbox me. Alright. Enjoy your afternoon. Thank you for taking time. Okay.